Hey everyone. So in this lecture, we're actually going to be focusing on measures of spread, but I want to just prime you guys again to remind you that these measures of center are going to be the one number that best captures that column, right? And it's going to vary based on the level of measurement you have, what kind of central tendency you can use. And we can do this by hand, or as I showed you in the last lecture, the one that included a little bit of R, you can calculate it also quite quickly using statistical programming. Now, I think it's always best to know the mechanics of how to do it by hand, but also just know that we're going to be moving into a place where you can do this via statistical computing and things are going to get a little bit easier. There's going to be less of doing this by hand and more about learning how to code, which should be really fun for you guys. So moving on from measures of center, we need to know whether that measure of centrality is actually a good representation of what's happening with that column. And so we need to then calculate our different measures of spread. So we're going to start with variance. Now, more often than not, we're using standard deviation as compared to variance, but it's easier to first calculate the variance and then calculate the standard deviation if we're going by hand. And you'll see why here in a second. So the variance is the average squared distance between every number and the mean. So we're taking the relative distance from every other number in the set to the average. This is going to show us how far our values are off from our measure of central tendency. So it helps us see how well the mean is going to represent the data as a whole. So it's the sum, right? This crazy sigma that we've already seen. It's the sum and squared difference of every value of x minus the mean. And mean, I want you guys to get this in your head, is usually most often visualized as x bar, right? So the x bar here on the right-hand side, that's the mean, and the x is just representing the other observations. We're then going to divide by our total number minus 1. This just does a little bit of correction for us. But I want you guys to focus on this general concept that it's the average square distance between every number and the mean, and it helps us see how well the mean represents the data as a whole. And so I'm going to give you a walkthrough, and then I'm going to give you a new set to go ahead and then calculate. So if we have this set, right, we're going to use this idea of C, right? C is the way we talk about sets in R. So that's why I want to kind of get you guys used to that language. So the numbers that we have in our sample are 3, 5, and 7. So if we're to calculate the average, right, 3 plus 5 plus 7 divided by 3, so 15 divided by 3 is 5. We have an average, right? So that's going to be our x bar. Then we're going to minus each value from our average and square it. So 3 minus 5 squared is 4. 5 minus 5 squared is 0. 7 minus 2 squared is 4. And then we have all of our square differences. We're going to add them together and divide them by our total sample minus 1. So we have our total sum of square differences, which is 8, divided by n minus 1. So in this case, it's 3 minus 1, which is 2. 8 divided by 2 is 4, right? And so we're doing the average square distance between each number and our average, with our average being 5. And then we're going to divide by the total number minus 1. So let's try to do this on your own with this set right here. 2, 5, and 8. You're going to start by calculating the average. You're then going to go ahead and take the sum of square differences for each. You're going to add those up, and then you're going to go ahead and divide by n minus 1. Pause here and calculate on your own. Okay, I'm assuming you paused. We're going to keep moving. So our average in this case is also 5, right? We added up 2, 5, and 8 divided by 3. The first value that we have to minus by 5 is 2. So 2 minus 5 squared is 9. 5 minus 5 squared is 0. 8 minus 5 squared is 9 again. 9 plus 0 plus 9 is 18. We're going to take 18 and divide it by n minus 1, which is 3. And we end up getting 9. So n minus 1, which is 2, excuse me. So 18 divided by 2 is equal to 9. So our variance in the first case is 4. Our variance in the second case is 9. Now, why did we square things? I'm going to pause, let you guys think about that for a second. Why did we square things? Squaring allows us to get rid of that negative value that we often see when we're subtracting any observation from the average. So anytime that observation is smaller than the average, we're going to have a negative value. We need to get rid of that. So we've now brought it into this square dimension, right? Everything is squared. And that inherently makes your variance a little bit harder to interpret in terms of the original set. So a variance of 9, right, as a measure of spread doesn't make a whole ton of sense in understanding how far away 2, 5, and 8 are from each other, right? It gets a little bit complicated at that point because it is not inherently clear how 9 relates to all of these, right? And the same goes for our set of 3, 5, and 7. While it's a little bit better, it's still not very indicative of the difference. But we had to square in order to get rid of the negative. So how would we then go about getting to a measure of spread that's a bit better representative of the set we originally had and doesn't have a negative? We need the standard deviation. So the standard deviation is the average distance between every number and the mean, still getting the variance, but then we actually just square root the variance formula to get the standard deviation. So the standard deviation is just the square root of our variance. So it's essentially the same way. It's going to show us how far off most of our data is from the mean, but it's going to do it in such a way that's much more intuitive logically. So in the last case, we had a variance of 4. If we square root that 4, our standard deviation is 2. The difference between 3 and 5 is 2. The difference between 5 and 7 is 2. So we're now back in a dimension where it actually is representative of the spread of the set. And we don't have a negative, which is great. So this is why most of the times when we're talking about measures of spread, we're talking about the standard deviation and not the variance. But we have to calculate the variance first in a lot of ways because we need to get rid of the negative value. So pause right here, do this example with the next set. It's also the same example from the last set, so you can use the variance that we already had. You can pause and then keep moving. So if we have a variance of 9, we're going to square root 9, which is 3. And guess what? The standard deviation of 3 makes a whole lot of sense. The difference between 2 and 5 is 3. The difference between 5 and 8 is also 3. So we're now in a dimension that makes a ton of sense, which is why we want to use the standard deviation as a measure of variance. Now, the last measure of spread that we have is the range. The range is the least informative, kind of not preferred version of this, but if we have something like ordinal or the nominal, we may have to do something like this. So we can also do it for interval ratio, but it's much more limited, so we can only do it in certain contexts. So say we have this set of 3, 5, and 7. We're going to take the lowest and we're going to take the highest number, the lowest number being 3, the highest number being 7, subtract them from each other. 7 minus 3 is 4. So we have a range of 4. So it shows us how big the set is, but also doesn't give us very good understanding of the differences between each of the values relative to the measure of centrality. And so it's not precise in a lot of ways. So we prefer to be in cases where we are operating using either the standard deviation or the variance. And remember that the standard deviation is usually our preferred because it makes a little bit more sense in terms of the actual set. So we have measures of central tendency, mean, median, and the mode. And then we want to see if that central tendency is a good fit. So we want to see maybe if our mean is a good indication of what's happening with our data. So we'll calculate the variance and the standard deviation to find out if it is and how much spread there is. Again, all this stuff is pretty approachable by hand, but also it can be done fairly easily in R. So moving forward, I'm going to teach you guys how to do that in R, but now you have this good foundation on how to do it kind of by hand to kind of work the mechanics in.